see many new faces as well. Yeah, this, for those of you who've been here before, it's really always fun and very interactive here at Simons, and hopefully the rest of you will experience it too. So this is slightly unlike a usual summer cluster in the sense that it's really larger, so it's more like a semester program, but half the length. So that's what we have this summer, and yeah, it's being organized with Urmila and Sandy and Bill and Chinmay. And during the semester, we'll have a workshop in mid-July, and then we have the usual thing, which is a brainstorming seminar, which will be on Wednesday afternoons at 2. So not tomorrow, but starting next week. Okay, so if you'd like to speak in that, please let us know. So one of the things that we decided to do this summer on an experimental basis is to have this sequence of one-day workshops, and the thinking behind this was, one of the nicest things about the Simons Institute is that it gives everybody a chance to collaborate, and these brainstorming sessions were a way to get everybody involved in some topics, but the thought was we could do this a little more formally through these one-day workshops, which would each be focused on some topic of interest, ideally where there's an interesting open question or few open questions. And so the idea is that these one-day workshops are a way of getting people up to speed on that open question. It's hard if you're starting from scratch to get up to speed on a research topic. And so the fact that we have so many experts here to help us get up to speed, this is really an opportunity. And then the other thought was that a full week workshop is sort of an embarrassment of riches, because no sooner do you get interested in a question on the first day that on the second day you hear something else and it knocks the first day out of your mind, and so on. And so this sort of more focused one-day workshop is a way to to get up to speed on a topic, and then actually have the rest of the week to collaborate with others or start thinking about it. And so it's a little bit of an experiment, and each workshop will be probably run in a slightly different way. And by the end of the summer, we'll hopefully understand how to do these well, and try to take that forward to the spring program next spring. Okay, so I guess today's workshop is probably exemplified by this title here, even though the workshop title says something different. And of course, Tomoyuki Marumai is who is giving the first talk, also helped put together the schedule for the workshop. So thanks, Marumai. Please, looking forward to your talk.
Thank you very much for the nice introduction. And also, first, I'd like to thank organizers of this program, quantum computing program. So this mini workshop is just for some minimum assumption for cryptography. And now I give some basic introduction to this field. So first, in classical cryptography, as you know, one-way functions are the minimum assumption. So this is a very well-known fact over 3 years, more than 3 years. And this is because we have many primitives like one-way functions, pseudorandom generators, commitments, digital signatures, and so on. And all these primitives are equivalent to one-way functions. Okay? So you can construct these primitives from one-way functions. And also, these primitives imply one-way functions. Okay? And also, we have other primitives like public key encryption, multi-party computation, and so on. And these primitives will not be constructed from one-way functions, but still they imply one-way functions. So this means that if one-way functions do not exist, almost all classical crypto primitives do not exist. And because of this, in classical cryptography, one-way functions are the minimum assumption. So natural question is this also the case in quantum cryptography? So one-way functions are also minimum assumption even in quantum cryptography. Okay. And actually in quantum case, we have many nice advantage. So for example, we know that key exchange is possible without any computational assumption. Okay. In classical case, we need some assumption which is stronger than one-way functions. But in quantum case, we don't need any assumption. Okay. Also, in classical case, a constant round statistical hiding commitment is known to be impossible from one-way function in black box case. Okay. But in quantum case, you can construct a non-interactive one from one-way functions. Okay. Also, now we know that even multi-party computation is possible from one-way functions. So in classical case, they are in cryptomania. So maybe we need some stronger assumption than one-way functions. But in quantum case, you can construct multi-party computation from one-way functions. Okay. And also, even public key encryption is possible from one-way functions if you can send quantum state. Okay. So in this way, and so we have many nice advantage in quantum case. And also, we have some new primitives which do not have any classical analog, like certified deletion or quantum money or one-shot signature, quantum copy protection. Okay. So these primitives do not have any classical analog. Okay. So in this way, we have many nice advantage in quantum case. But still, most of them use one-way functions. Okay. Or even much stronger assumptions like IO or something like that. Okay. So natural question is, are one-way functions the minimum assumption even in quantum cryptography? So we have this question. And actually, the answer seems to be no. So this is the main message of this talk. So actually, in quantum case, one-way functions are not necessarily the minimum assumption. Okay. And so Kretschmer pointed out some possibility of quantum cryptography without one-way functions in his paper, 2021. And then two papers constructed some primitives without one-way functions. And also now we have many papers about this topic, including even some application to black hole physics. Okay. So now I explain some three basic primitives, assumptions that are often studied in this field. So we have pseudo-random state generators, one-way state generators, and EFI. Okay. So first, this pseudo-random state generator is just a quantum analog of pseudo-random generators. So PRSG is just some quantum polynomial time algorithm that outputs m qubits quantum state on input n-bit string k. Okay. And security is defined as follows. So the challenger chooses single bit b, and if b is equal to 0, the challenger samples n-bit string k uniformly at random and generates t copies of this phi k. Okay. Then challenger sends these t copies of phi k to the adversary, QPT adversary. If b is equal to 1, the challenger samples t copies of her random states. This is just completely random pure states. Okay. And then this state is sent to the adversary. And the adversary must decide whether given state is this pseudo-random state or just a completely random state. Okay. And the security means that no QPT adversary can distinguish this and this, except for some negligible advantage, even if the adversary receives polynomially many copies of this quantum state. Okay. So this is just, you can see, this is just quantum analog of pseudo-random generators. So this is not completely random states, and this is completely random states, and no QPT algorithm can distinguish them. Okay. And in this paper, they constructed pseudo-random state generators from quantumly secure one-way functions. And also there are some constructions, another constructions given in this paper. By the way, if you have some question, maybe you can ask anytime. So second one is one-way state generators, which is quantum analog of one-way functions. So this is just quantum polynomial time algorithm that outputs m qubit states phi k on input n bit string k. Okay, and security is defined as follows. So the challenger first samples n bit string k and generates t copies of this phi k. And then this state is sent to the adversary, QPT adversary. And adversary must return some n bit string k prime. Okay? And the challenger check whether this k prime is a correct preimage or not. So here, correct preimage means challenger measures this quantum state in this basis, and then accepts if this result is obtained. If this projection is successful, he accepts. And the security means that the probability that the challenger accepts is negligibly small. So intuitively, this means given this quantum state, no QPT adversary can find correct preimage. So this is just a quantum analog of one-way functions. Okay? And actually, this one-way state generators can be constructed from pseudo-random state generators, which I explained in the previous slide. And also in classical case, we have some variants of one-way functions, like weak one-way state generators or distributional one-way state generators. And in classical case, they are all the same. Okay? So weak one-way function implies standard one-way function, and distributional one-way function implies standard one-way function. And in this quantum case, it was shown that they are actually also equivalent to one-way state generators. Okay? So the third assumption is EFI. So this is just some QPT algorithm that outputs m qubit state rho b on input a single bit b. Okay? And the output must satisfy the following two properties. So firstly, they are statistically distinguishable. Okay? So just they are very different states. Okay? So in principle, you can distinguish these two states. The second property is they are computationally indistinguishable. So no quantum polynomial time algorithm can distinguish this rho 0 and rho 1. Okay? And this is the definition of EFI. And
Sorry, can you go back to the previous step?
Yep.
I missed how it differs from the random quantum states.
Yeah. So this is just a QPT algorithm that outputs m qubit quantum state on input classical data. And security is intuitively given this state, you cannot find correct k. And this correct means, of course, this exactly this k, and also another k that is very close to this k in the sense that this state and this state are close. So in quantum case, we need this type of additional property because states are non-orthogonal. Okay. So this EFI is just, so classical version of this EFI was introduced long ago by Goldreich, and he showed, so this classical version is just two classical distributions that are statistically far, but computationally indistinguishable. So he defined this classical version of EFI, and he showed that this classical version is equal to one-way function. So in classical case, just this is equal to one-way function. Okay. So I have introduced three assumptions or primitives, and now I explain why they are interesting. Okay.
What does EFI stand for?
Yeah, so actually I don't remember. so every time I am asked that, so maybe they should have chosen another data. so I think E stands for efficient. So this rho 0 and rho 1 should be generated efficiently. And also F means far, and also indistinguishable. I guess maybe you can ask. Okay. Yeah, okay, so now I explain why these primitives are interesting. So first reason is they seem to be weaker than one-way functions. Okay, so as I said, PRSG can be constructed from one-way functions, and also one-way state generators can be constructed from PRSG. Okay, and PRSG trivially imply one PRSG. This is just a PRSG where only single copy is given to the adversary. So in this PRSG, polynomially, any polynomially many copies are received to the adversary. But in this case, just only single copy is given to the adversary. And also this one PRSG trivially imply EFI because, yeah.
I guess you would need a length extension requirement though, right? You would need that the output in the one PRSG that the output is longer than
Yeah, sure. Yeah. Otherwise, you can construct one PRSG trivially. Just so, I mean, if the output length is shorter than input length.
Right, but the PRSG doesn't necessarily satisfy that originally.
Yeah. Okay, so yeah, actually, so that's good point. So yeah, so in that sense, maybe this should be more precise. So you are right. Yeah. But if just we forget that point, this just intuitively implies this one because if this is secure for many copies, of course this is secure for single copy. But your point is, yeah, actually that's correct. So anyway, we have this relation now, and actually it seems that we have some distinction between this one-way function and other primitives because there are two papers that suggest this separation. So first paper showed that pseudo-random state generators exist even if BQP is equal to QMA. So if BQP is equal to QMA, NP is in BQP, and in this case, no quantumly secure one-way function exists. But still, PRSG could exist, according to this paper. A second paper, recent paper, showed that one PRSG could exist even if P is equal to NP. And so again, if P is equal to NP, we don't have any one-way function, but still this primitive could exist. And so this result suggests that these new primitives seem to be weaker than one-way functions. So maybe we have mini-crypt where one-way function exists. Maybe we can define some word micro-crypt where one-way functions do not exist, but these primitives could exist. Okay, so I'm not sure whether this micro is a better name, but just I googled and maybe micro is some word smaller than micro, mini. So maybe if you have some nice suggestion, maybe.
We have crypt C.
Sorry.
And the next generation will be crypt C.
Crypt?
Crypt C.
Crypt
Like
C.
USB-C is now.
Yeah, okay, so anyway, so what I want to say is, so we have another word where one function do not exist, but still these primitives exist. So this is one reason why this is interesting. And the other reason is they are actually useful. So now we know that many useful primitives can be constructed from these micro-crypt primitives. So for example, privately verifiable quantum money can be constructed from PRSG. And also secret key encryption is possible from PRSG. And also digital signatures is equivalent to one-way state generators. And also non-interactive commitment, so statistical hiding or statistically binding. So both flavor of non-interactive commitments is equivalent to this EFI. And because commitments imply multi-party computation, this also means that EFI also implies multi-party computations. Okay? So in this way, we have many nice applications of these primitives. Okay, so just as an example, I explain some construction of primitives from these micro crypt assumptions. So one example is construction of computational hiding and statistically binding commitment from one PRSG. So we have sender and receiver, and sender wants to commit a single bit, 0 or 1. So if the sender wants to commit 0, he generates this quantum state. So this is just a superposition of all k state, and he coherently run this PRSG algorithm to generate this phi k. Okay? If he wants to commit 1, just sender generates this maximally entangled state. And sender sends only this C register to the receiver. This is a commitment. Okay, this is the end of commitment. And then in the opening phase, sender sends single bit B, which he committed, and also this R register to the receiver. Okay. Then receiver check whether this state is actually this state or not. So she can do this just applying inverse of this QB and measure all qubits and check whether result is all 0 or not. Okay. And so we can easily show computational hiding and statistical binding. So for computational hiding, what we have to show is a reduced density operator on this C register are computationally indistinguishable. So because in commitment, only this C register is sent to the receiver, but the receiver cannot distinguish these two states. And this is just by the definition of one PRSG. Okay, so this is just one PRSG state, and this is maximally mixed state, just a high random state, single copy high random state. So by the definition, they are computationally indistinguishable. And also for statistical binding, actually what we have to show is this reduced density operators on C registers are statistically far. This is just statistically far. And actually, if you can show this, you can also show some binding, for example, some binding. And so intuitively, why this is enough for binding is if this C register are far, then this sender cannot change this state to this state by acting only on this R register. If C are far, this is just Ullmann's theory. Okay, so in this way, we can construct computational hiding and statistical binding commitments. And also, we can change this flavor by using these results, and we can get statistical hiding and computational binding commitments as well, and also non-interactive one. Okay, and second example is a construction of digital signatures. And to explain this construction, first I just review classical construction of digital signature from classical one-way functions. So this is just a textbook example, which is known as Lamport signature. So F is just a one-way function, and the secret key is some randomly chosen bit strings, K0 and K1. And public key that is used for verification is just F of K0 and F of K1. And the signature for message 0 is just this K0. And the signature for message 1 is just this K1. Okay? And the verification is just verifier compute this signature, compute value of F on this signature and check whether this is equal to public key or not. And security is just to come from the one-wayness of this function. So the adversary can get this public key, but because this is a one-way function, so he cannot compute this preimage from this Fk0 and Fk1. And just we can use this idea. And so instead of this one-way function, we use one-way generators. So just a public key is phi k0 and phi k1. Okay. And again, because of the one-wayness of this one-way state generator, no QPT adversary can find correct k0 and k1. That's why this is secure. But this construction is only one-time secure, which means you can sign only once. And in classical case, you can construct many times security, many times secure one from this one-time secure one. Okay, but just this technique cannot be directly used for this case. For example, because public key is now quantum state, and we don't know how to sign quantum states. So in classical case, just use sign public key, and just you can construct many times secure signatures. But in this case, I don't know how to do that because PK is quantum state. So this is an open problem whether we can construct many times secure signatures from PRSG. One-way state generators. Okay, so finally, I explain some open problems. So first open problem is, of course, what is a minimum assumption in quantum cryptography? So now it seems that one-way SG and EFI are very minimum assumption because all imply these two primitives. But there could be some another one, which is implied by everything, which I say ultimate quantum assumption. Okay, but unfortunately, at this moment, I don't know what is this.
Is it possible that there's no single minimum assumption? There are like many assumptions that are only
Yeah, exactly. So just I'm saying. So instead of this unique ultimate assumption, maybe this is just very chaotic and we don't have any single unique assumption. That could also be possible. Yeah. But maybe this should be more interesting. Yeah. But I don't know which happens. Okay. So another open problem is to find some more relation between these primitives. So for example, I want to know whether one-way SG imply PRSG. So in classical case, one-way functions imply pseudo-random generators. But in this case, I don't know how to show this. So because in classical case, one-way function implies PRG, so maybe one-way SG should imply PRSG, but at this moment, I don't know how to show this. And the other interesting question is, so one-way SG is equivalent to EFI. So in classical case, as I said, Goldrake showed that classical version of EFI is equivalent to one-way functions. But in this quantum case, I don't know how to show this. Okay, and also I'm interested in the construction of PKE from these microcrypto primitives. So just we have constructed almost all primitives from these microcrypt primitives, but remaining one is public key encryption. So I don't know how to construct a quantum public key encryption from this microcrypto primitives. Actually, recently we constructed PKE from one-way functions, but it is open whether we can weaken this assumption from one-way function to some more weaker primitives. And so in this case, for example, so in our construction, public key is just a quantum state. And in this case, somehow we can hide some nice trapdoor. And that's why we need only one-way functions. But in this case, public key is quantum state. And usually quantum channel is not authenticated. So we should authenticate this quantum channel. But in this case, maybe we need a signature and we need a one-way function. So I don't know how to construct this public key encryption from some weaker assumptions. Okay, and also, I'm interested in what is a quantum version of one-way function. So I introduced the one-way generators, which is just some quantum polynomial time algorithm. So input is classical data and output is quantum data. So this is a very reasonable quantum version of one-way function. But still, we could define some more another variant, like this is just a quantum polynomial time algorithm that output quantum state and classical data. And security is given this quantum state, you cannot find this classical data. So in this case, there is no random seed. Okay? So in classical case, you need some random seed. But here, just this is, we don't have any random seed. So this should be very different from quantum classical case. And also, even we could consider some algorithms that output two quantum state, and security is given this quantum state, you cannot find this quantum state, or even they could be entangled. Okay, so in this way, we can consider many another variants of quantum one-way functions. Okay, and also I'm interested in what is a classical complexity assumptions necessary for these primitives. So we know that P is not equal to NP is necessary for one-way functions. Okay? But for these primitives, we don't know anything except for the result by Kretschmer, so who showed that PP is not equal to BQP is necessary for PRSG. Okay, but for other cases, I don't know how to show similar result. And one reason is shadow tomography technique cannot be used here. So shadow tomography is just some technique where so you are given T copies of quantum state and you run some QPT algorithm, and then you get some classical data. Okay, and once you get this classical data, you can do some very long classical computation to compute this quantity. So just a projection of given state onto some pure state for any set of pure state. Okay? And great advantage of this shadow tomography is the number of samples is just a polynomial, even if this large M is exponentially many. Okay? And he used this technique to show that PRSG are broken if BQP is equal to PP. So idea is as follows. So that adversary receives T copies of quantum states, which is PRS or half random state. Okay, and then adversary run quantum polynomial time part of this shadow tomography and get some classical data. And just adversary sends this classical data to Oracle, which can decide this or this. So there exists some k such that this is satisfied, or for any k, this is equal to 0. And if given status this PRS, this is satisfied because there exists such k. Okay, but if given state is half random state, this is satisfied because there is no such k. Okay, and this Oracle decide this and sends decision bit to the adversary. Then adversary can distinguish these pseudo-random states and half random states. And what Kretschmer showed is that this Oracle is actually PP. So PP is enough for this decision. Okay. So in this way, just we can break PRSG, but for these primitives, we don't know how to use shadow tomography, because in this case, the adversary gets only single copy of quantum state. And in order to do shadow tomography, you need polynomially many copies of quantum state. So for this case, I don't know how to use shadow tomography. Okay. So finally, just I mentioned, maybe so instead of classical complexity class, we can consider quantum complexity class. So we have many classes like PNP, P-space, BQP, and QMA. And BQP and QMA are often considered as quantum class, but still they are classical in the sense that inputs and outputs are classical. Okay? But maybe we can define some complexity class, quantum complexity classes, where inputs or outputs are quantum state. And maybe we can study some complexity for generating quantum states or complexity for distinguishing quantum states. And this type of quantum complexity class should be more suitable for the study of cryptography, quantum cryptography, because in quantum cryptography, adversary gets quantum state instead of classical data. Okay, so finally, in summary, I first mentioned that one-way functions are the minimum assumption in classical cryptography. But in quantum case, this is not necessarily the case. So one-way function is not necessarily the minimum assumption. And actually, we have PRSG, one-way SG, EFI, and they seem to be weaker than one-way functions, but still they have nice applications. And of course, most important open question is what is the minimum assumption in quantum cryptography? Okay, thank you very much for your attention.
Thanks, Tomoyuki. Any questions?
Not a question, but a small answer to earlier. EFI seems to stand for efficiently sampleable, statistically far, and computationally indistinguishable. So they only took half of the words for the abbreviation.
So let's move on to the next speaker.